Hi everyone, I'm Keshav Giri, application engineer for Mirabilis Design, and today I'm going to be walking you through architecture exploration of ARM Corelink CMN mesh networks using VisualSim. So there are three kinds of CMN mesh networks in the market right now: the CMN 600, the CMN 700, and the CMN Cyprus. And going through the differences between these networks, with each iteration of the CMN mesh, ARM has increased the capacity, the scalability, the number of cores supported by the mesh network, the total system level cache sizes supported in the mesh, the number of memory controller devices that are accommodated on the mesh, and providing enhanced multi-chip connectivity. So we can see that on the CMN 600, the maximum mesh size available was 64 nodes, which has now been increased to 144 nodes. Previously, only 64 cores were able to be connected to the mesh, but now we can connect up to 256 cores per die. The total SLC size in the CMN 600 mesh was 256 megabytes, which has now been increased to 512 megabytes on the CMN 700. And the introduction of the super home node or the HNS in the CMN Cyprus for managing address spaces. In the CMN 600, we could connect up to 16 memory controller ports, which was increased to 40 on the CMN 700. And on the CMN Cyprus, it supports coherent multi-chip links for efficient communication. The CMN 600 provided up to 4 CCIX ports for coherent connections, which was expanded to 32 ports on the CMN 700. And now let us take a look at how the CMN mesh network can be modeled in VisualSim. So VisualSim is shipped with library components that can be used to model either the CMN 600, the 700, or the Cyprus. It contains a complete list of all the CMN interface devices, and the library modules present in VisualSim provide a scalable, configurable interconnect where each device can be configured through a list of parameters. The current design is based on the Corelink cache coherent network, which enforces a cache coherency mechanism in a system with multiple IP cores. We are also able to choose the routing scheme in the mesh network, and the choice is between a static routing or an XY routing. VisualSim also lets you configure a system address map to be able to assign a home device for any incoming request based on the address range. So looking at the kind of trade-off analysis you can do on VisualSim, since the device parameters, the mesh size, the topology, and the device connectivity can be exhaustively tested by performing any modifications that are required, the mesh can be tested for buffer occupancies, the latencies for individual request completion, the throughput at any device present on the mesh, and many other statistics. After comparing all of these statistics, the best possible mesh configuration can be selected before moving to development and integration. Let us go through the individual blocks present in the Corelink CMN library in VisualSim. So VisualSim provides a list of the requester nodes, home nodes, hybrid nodes, and other devices present as interfaces to the CMN mesh network. With regards to the requester nodes, we have the RNF, RNI, and RND. With regards to the home nodes, we have the HNF, which is fully coherent, the HNI, HND, the SBSX, which is used to connect to a memory device, the SNF, which is a fully coherent slave node with a memory device present in the node, and also the HNP, which lets you interface with a PCIe bus, and the HNS, or the super home node, which is present in CMN Cyprus networks. The HNF library block present in VisualSim can be used interchangeably to implement a HNS. We also have the CCG or the CCIX gateway, which lets you interface with the CXL device, and also the CAL device, which is a component aggregation layer, which lets you accumulate incoming requests from multiple request nodes. For other devices that are connected to the CMN interface blocks, VisualSim provides library implementations for the AMBA, AHB or APP bus, the XI bus, the ACE bus, the latest CXL 3.0, the latest iteration of the PCIe Gen 6, multiple implementations for TDR and LPDDR memories. We have the HBM 2.0 and 3.0 memories, various SoC components, processor cores, storage buses, and network interfaces. Now, let us take a look at how the CMN library blocks can be configured in VisualSim. So the Corelink interface blocks and the XP router are available as library components that you can drag and drop onto the GUI interface in VisualSim, where you can make connections between these blocks and run a simulation. Each of these blocks is configurable through a set of parameters, and the Corelink setup block is used to set mesh level configurations. So as you can see here under the library, we have the interfaces and buses where we have the Corelink library blocks. So let us first take a look at the Corelink setup block, which lets you set mesh level configurations with CMN network. So the Corelink setup blocks lets you configure the routing algorithm for the mesh. In the case that the choice is a static routing algorithm, the static routing table present in the Corelink setup block will be referred to when routing any request across the mesh. In the case of an XY routing, it will follow the shortest path algorithm based on moving in the X direction first and then the Y direction. There is also a global system address map defined as part of the Corelink setup block, which is used to route the request to the appropriate home device based on the address value and the address range is defined. The bandwidth for each VLAN ID can be defined through the VLAN database, and quality of service regulation and reservation can be defined based on the quality of service value. The statistics for the requester devices and the routers can be viewed by setting a toggle on the Corelink setup. So we can see here, we can set the routing algorithm, the register value selection for the quality of service, the quality of service database, the VLAN database, the global system address map, and the static routing table to be followed. So when a request has to be routed from HNF1 to RNF1, it will follow the path defined in the static routing table. And we'll also be able to view the latency, buffer occupancy stats, and the throughput stats by setting these toggles over here. The next device that we'll look at is the XP or the router. The XP blocks within the SoC are used to send the incoming requests and data to the right device by reading the destination field present in the packets. And as mentioned before, the routers support two types of routing methods, the XY routing and the static routing. There are 4 channels defined for the packets, and according to the channel type, each message is given a delay and then sent out to the next router or the end device. On starting the simulation, each interface device connected to the XP will send a hello message to create a record of where these devices are present in the overall mesh. Each XP can support up to 4 devices. They can be requester, home, slave, master, initiator, or target devices. And if you look at the parameters for the XP device, we are able to configure the buffer sizes, the router frequency, the router width, and enabling flow control on output from the router device. Router device is present in the library under the name XP, and we'll be able to set the configuration for the XP by double-clicking on it. Next, we'll look at the request nodes. So we have the RNF, RNI, and RND. The RNFs are traffic sources that create and pass requests to the appropriate home nodes. The RNIs are simple traffic generators that create data requests for non-shared memory regions. So they do not provide snooping support at the HNF or the HNS. And the RNI is the interface implementation for the AMBA Chi-Fi IP for the Corelink CMN mesh. The RNDs have the same functionality as the RNI with added DVM support. The destination of any incoming packet to the requester nodes is obtained by reading the system address map present in the Corelink setup block. And based on the system address map, the incoming request will be routed to the appropriate home device. And for each of the requester nodes, we'll be able to configure the device frequency, the VLAN queue, the buffer sizes, the request priority for requests that are coming out of this requester node, and the flit sizes for the outgoing requests. We can also choose an option to assemble the outgoing flits at the slave device. So we can see the implementation for the RNF, RNI, and RND. All of them have similar parameters with regards to the device frequency, the VLAN queues, buffer sizes, request priority, and flit sizes. Next, we'll take a look at the home nodes. So first, we'll take a look at the HNF and the HNS. So the HNF library implementation can also be used as a HNS device. So the HNFs act as a smart memory interface within the NOC. They receive and process incoming requests from the home requester nodes. The HNF also stores all the incoming requests in queues based on the quality of service. It then uses an arbitration algorithm that uses wait times and round robin arbitration on the incoming QoS classes to pop the right queue at the right time. And the HNF also has an internal database that is updated for every request to be able to facilitate snooping. And based on the type of request, the home node reacts differently. So there is also a cache slice present within the HNF or the HNS, which can be configured. And for the cache slice, we'll be able to set the device frequency, the cache size, the cache width, and the NV associativity for that cache. There's also a snoop filter present within the HNF, which can be configured. And the system level cache can be disabled so that the HNF or the HNS can work with just the snoop filter turned on. The HNF or the HNS can point to a specific memory device in case there is a cache miss. Next, we'll take a look at the HND, HNI, and the HNP. And all of these function as home nodes. The HND has DVM support, while the HNP is used to interface with a PCIe bus. For these devices, we'll be able to configure the flit size, the device frequency, and the buffer sizes. Moving on, we have the SNF and the SBSX. So these devices are used as interfaces with memory components. The SNF has a main memory located within the node, while the SBSX acts as a bridge between the CMN mesh and slave memory devices. The memory within the SNF can be configured through parameters. We'll be able to set the memory size, the memory speed, the VLAN queue, and the buffer size. The SBSX can be used to enforce flow control between the CMN mesh and the slave memory device. Next, we have the CCG, which functions as both a requester node and a home node. So both the requester and home devices are connected across a CXL on the external interface. And for the CCG, we'll be able to configure the flit size, the buffer size, and the device frequency. For outgoing requests, we will also be able to configure the VLAN queue and the request priority. Next up, we have the content aggregation layer or the CAL device. The CAL is used to arbitrate requests from multiple IO nodes into a single device port on the CMN mesh. The CAL can be connected to a maximum of 4 IO nodes. As far as the VisualSim configuration is concerned, each CAL device should have a unique CAL number ID, and we can also set the clock speed for the CAL device. Now, let us look at a simple 2x2 mesh example created using VisualSim. So by dragging and dropping these components into the GUI, we'll be able to create a simple mesh network with 4 router devices. I have 2 requester nodes connected to the XPs, a system level cache slice, and a memory device in the form of an SNF. So these 2 requester nodes are going to be creating requests and sending them into the mesh network. And when the request enters the mesh network, the XP is going to look up to the system address map defined in the Corelink setup block to be able to route that request to the appropriate home device. So in this case, based on the address map definition, all the requests are going to flow to the HNF or the system level cache first. In the case that there is a cache miss, the HNF is going to go to the SNF, which contains a memory device, and fetch this data. On fetching this data, the HNF will then complete the request and send it back to the requester. So in the case that we use static routing, the mesh network is going to use the routing table defined as part of the Corelink setup. So if this request is flowing from RNI1 to HNF1, it will follow the path R11, R12, which is it enters this XP, moves to the second XP over here, which is R12, before entering the HNF. In the case of XY routing, it will forward the request to the device if it is present in the same XP, or it will move it in the X direction until the X value is met, and move it in the Y direction until it reaches the device destination. So thank you for watching, and in a follow-up video, we'll be looking at a more complex example for a CMN Cyprus 4x4 mesh built using VisualSim. Thank you.